Hello everyone, welcome to screencast SC20001. In the previous screencast we demonstrated how to run a throughput test using independent VLANs. In this screencast we are going to be demonstrating how to run a throughput test in extended VLANs, which essentially means all the packets get tunneled back to the controller and the controller then bridges or routes those packets to the desired destination. We are going to be using the exact same config that we used in the previous screencast, so let's get started. Our topology consists of an AP which resides on management VLAN 1. The RF switch essentially has two VLANs, VLAN 1 and VLAN 6. VLAN 6 is our data VLAN. All the servers, in our case iPerf and Chariot, will reside on VLAN 6. When a wireless LAN is created, we will map it to VLAN 6. Hence, all traffic destined from a wireless client to VLAN 6 would get tunneled back to the RF switch from the AP. And the RF switch would decapsulate those packets and route or bridge them to the right destination. The key components in our network are the RF switch with the AP650 or the AP731. We are using a wired gigabit switch for routing all the packets. A wired laptop is used to run the iPerf or Chariot software, and we have a wireless laptop which has the Intel 5300 chipset installed in it. We are using the Intel 5300 chipset because of its capability to transmit and receive packets at 300 megabit data rates, the full 802.11n rate set. Our software components are iPerf or Chariot. Since we are going to be using an extended VLAN, this VLAN is going to reside only at the controller and not at the AP. Hence, we will have to log into the controller, choose GE1, and make it a trunk port with VLAN 1 and 6. To create a trunk port on the RFS 7000, we will navigate to Configuration, click on Devices, choose our RFS 7000, double click on it or click on Edit, go down to Interface, click on Ethernet ports. As you can see, we have all our GE1 through GE4 ports here, as well as the ME1 port. We have our cable connected on GE1, so we want to edit that. So let's click on Edit. What we need to do here is make it a trunk port. So let's click on Trunk, let the native VLAN be 1, and the allowed VLANs will be 1 and 6, which is going to be our data VLAN. Click on OK and click Exit. So as you can see, we have allowed VLANs as 1 and 6. We do not necessarily have to create a VLAN 6 and give it an IP address because we are just going to be bridging packets on VLAN 6. So we are not going to be creating an L3 SVI. Let's commit our changes and let's hit save. Click on exit. In order for VLAN 6 to be an extended VLAN, it has to be defined somewhere in the config. Hence, in WiNG5, we have introduced a new policy called the bridging policy. The bridging policy essentially defines how packets are routed within devices, either local bridging, where all the packets are routed locally by an AP or a switch, or by extended VLANs, where packets are tunneled back to a certain switch. By default, the RFS switch and the AP are configured to function the independent VLAN mode, where everything is bridged locally. To create an extended VLAN, we will navigate to Configuration, go to Profiles, click on our bridging policy. There is a default bridging policy, so we're just going to go ahead and edit that. As you can see, we have basically wireless and wired bridging enabled by default, which means that the AP and the switch will just route packets locally. If we want to extend VLANs, we'll have to specify our VLAN ID that needs to be extended. So let's click on extended VLAN 6 and extend that VLAN all the way to the controller. Commit our changes, save it, and exit out of here. We will now create a new wireless LAN, assign it an SSID, map our extended VLAN 6 to this wireless LAN, secure the wireless LAN using CCNP, and finally map it to the radio. We are now going to create a new wireless LAN which is going to be extended to the AP. To do so, we'll navigate to Configuration and click on Wireless. As you can see, we already have our old wireless LAN from our previous screencast, which is the Moto CCNP. This is an independent VLAN where everything is bridged locally. To create an extended wireless LAN, we're just going to go ahead and create a new one. Call it Moto Extended. Let's call the SSID the same, which is Moto Extended. We are going to map it to VLAN 6. Click OK. Let's secure our wireless LAN with WPA2 CCNP. We will use the same password that we used before, which is Motorola. Click OK, commit changes, and save them. To map our new extended wireless LAN that we created, or rather the extended VLAN we created, we will navigate to Configuration, go to Profiles. We have two APs here, two AP profiles here. One is a 7131 profile and one is a 650 profile. Let's choose 7131. Let's click Edit. We are under Interfaces, Radios. As you can see, we have our radio 1. Let's click on Edit. From our previous screencast, as you can see, we already have our Moto CCNP wireless LAN advertised. Let's choose Moto Extended, bring it to the left hand side so that it gets mapped to the radio. Click Exit. Do the exact same thing for our 11A radio. Click OK. Click Exit. Let's commit our changes and let's save it. Let's navigate back to Profiles and go to 650 and map our wireless LANs to both the radios, just like we did with the 7131. Now we essentially have any AP coming into the network getting mapped to these two wireless LANs, the Moto CCNP and Moto Extended. Let's commit our changes and let's save it. We will now associate a wireless client to our Moto_Extended wireless LAN. This wireless LAN is mapped to VLAN 6, hence we will give our wireless client an IP address of 192.168.6.200. We will ping our wired server, which is 6.27, just to ensure there is connectivity between our wireless client and server. On the wireless client, we are going to run the iPerf server, where it is going to listen on a TCP port. The window size is going to be set to 256. On the wired server, we will run the iPerf client, where it will direct packets to 192.168.6.200. Hence, this is a downstream test, and the window size is again set to 256. Our TCP results with the Windows 7 and the Windows XP laptop, there is not much difference between the results. We are getting close to 190 megs in both cases. If we compare these results to our independent VLAN that we did in the previous screencast, you won't notice too much difference. There is definitely going to be a bit of difference, primarily because of the mint overhead involved in tunneling packets back to the controller. But as you can see, our TCP throughput is close to 190 megs, which is expected. To run a UDP test on the wired server, we will direct packets to 192.168.6.200, which is our wireless client. The -U option indicates it is UDP, and the bandwidth we are going to try and push is 300 meg. On the iPerf, on the wireless client, we will run the iPerf server, again with the -U option indicating it is UDP. Let's look at our results, UDP results. Again, as seen, our results are over 220 megs in both instances, irrespective of the OS that we've used. This is the expected result. Again, comparing this to independent, there could be a slight difference because of the mint overhead, but we are all in the same ballpark of 220 megs. You should now be able to run a throughput test using the RFS 7000 and the adaptive APs. The config for the RFS 7000 can be downloaded from the link seen on the screen. Thank you.